All right, last time we introduced some of the concepts that we'll be covering in the class at a very high level and did a good bit of set review. So I'm hoping that a good bit of that set review was in fact review, so that when we start to think about and write a little bit more mathematical language, won't require an immense amount of prep or discussion. But we're going to dive into a little bit more detail, kind of just an overview of the kinds of material that we will be talking about at a high level, but a little bit deeper than we went yesterday. So we'll start to formally define something like a language. I mentioned that a language consists of an alphabet. Further defining that, it's just a non-empty set of symbols. We're going to denote it with a capital sigma. As an example, the language, the alphabet in this particular language could just consist of A's and B's. It could also could be binary, zeros and ones, could be English, lowercase a through Z, uppercase A through Z, digits, punctuation. A language could be ASCII, language could be a programming language. And whatever symbols are allowed in that particular programming language are what's allowed in the language. One of the highly restrictive language, go look at white space, error, just spaces, tabs, and new lines. That's all that's allowed in the entire language. Very unreadable. But that would be the alphabet of that language. Strings are when we start to put together characters in the alphabet to form words, statements. We don't really use the concept of words in this class. We will use either tokens or sentences once they finally combine into something large enough to have meaning. But some finite sequence of characters from the alphabet. So ABBA could be defined as U. BABBABBABABAAAA could be defined as V. In this class, we're going to start in general with our toy languages, starting with A's and B's as the letters that are part of the alphabet of the languages that we talk about. And strings will start with U. So U, V, X, Y, Z, W is referred to in some other context, but usually U and V refer to strings. Exactly as mentioned here, like I know what's coming. So A, B, and C will name characters and alphabets. U, V, W will name strings for the moment. We can do all sorts of string operations, just like you would be used to in a programming language. Strings, reverse strings, define some particular subset of a string from some index to some other index of a string that becomes a substring of that string. We can query things like the length of a string, determine whether a string is a prefix or a suffix of another string. We will use the lambda to define the concept of empty string. So you see a lambda, that just means what you're used to in Java being quote, quote. It's not null, it is the empty string. W with a capital R superscripted is the reverse of a string. That's kind of strange notation. There will be a good bit of unfamiliar and strange notation probably at the start of this class. This is just, I utilized and I'm trying to stay consistent with the terminology and notation from the textbook in case those of you have the textbook and are following along with the textbook. But sometimes from textbook to textbook, you'll get slightly different notation. So I'll stay consistent with that. Superscripts usually mean other things in this class. Superscript R just means reverse. Superscript some number, that number being n, is repetition. So in Java, if you're concatenating something, you would have WW, which you will also see here if it's exactly two instances of W concatenated together. But you could also, in this case, say W squared to represent that same concept. All right, sigma is our alphabet. We can define this concept called the star closure of it. Sigma superscript star. This is all strings that can be obtained if you concatenate some legal string, some alphabet symbol, because this is the alphabet, with some other symbol in that alphabet some number of times, 0 or more. So the empty string is always in the start closure of an alphabet. If the alphabet is something like AB, then the start closure would be everything of length 0, the empty string. Everything of length 1, A and B. Everything of length 2, AA, AB, BA, BB. Everything of length 3, AAA, AAB, ABA, etc. And just continue that process forever. It's an infinitely large set. A superscript plus instead of a superscript star just says there have to be 1 or more instead of 0 or more. So it's the start closure of the alphabet minus the empty string, or I guess the set containing the empty string. So even though any particular alphabet might be finite, both the start closure and the positive closure are infinite. Anyone have an intuitive idea as to why that would be? I half described it, but
because strings can have an infinite number of letters. Or
yeah, even with an alphabet of size 1, you can just map that to the natural numbers. You can have 0 A's, you can have 1 A, 2 A's, 3 A's, 4 A's, 5 A's, and it just becomes the sequence that is the natural numbers. And since the natural numbers are infinite, then the size of the start closure is also infinite. And that's just for an alphabet of size 1. We throw in a second character, and now there are more. Well, it's actually the same amount. We'll talk about that later. It's also infinite. We'll define a language as some defined subset of the start closure of an alphabet. So if we had the start closure of the alphabet AB, I guess let's use binary, because binary is probably going to be a little bit more familiar. If we're using 0s and 1s, then we can define some language as a subset of all possible sequences of 0s and 1s. So maybe just all of the even binary numbers. That could be a subset. 111 is not an even binary number. Therefore, it would not be part of the language that we have defined, which is a subset of the start closure of the language of the alphabet binary. Does that make sense? Any other questions on that concept? We can define sentences within languages as just a string that is in the language. So strings are all legal concatenations of characters in the alphabet, but sentences are those that belong to a query language. We'll go back to AB for a second. So recall that a superscript n just means repetition n times. So the language that we're curious about here is a to the n, b to the n. Some number of a's followed by exactly that many b's. Since we're using the same variable here, n, as the superscript, it means the same number. If there were a different variable there could be different amounts. But since the same variable means exactly the same amount. So some number of a's followed by exactly that many b's. First of all, what's the start closure of the alphabet? How could we define that in terms of set notation?
Maybe this is too vague, but I mean the set of all strings that have 0 or more A's or B's in them anywhere, like A, AB, BA.
Could it be BA? For the start closure of the alphabet, yes.
Yeah, not for the language.
Yes.
For the.
So if we're defining this set, kind of already talked about this, but I like to order them in terms of their length, just because that makes sense. It gives an order to it. So we can use the ellipse to just start saying, all right, everything of length 0, everything of length 1, everything of length 2. And as soon as a pattern emerges, then you could state that. But you could say basically for any length, any sequence or combination of A's and B's. And we'll come up with a language that will easily be able to, or a language notation that will be able to do that in a little bit. I don't want to go quite that far ahead. So for now, that's good enough. So that's the star closure of the alphabet. How about some examples of sentences in the language?
A, B, B.
All right, I like it. A, B, B, that's in the language. What else?
A, B, B, B.
Sure. A, B, B, B is in the language. Couple more. What else is in the language?
A, B.
A, B is in the language. What's the easiest thing to write that's in the language?
Empty string?
Yes. A to the 0, B to the 0 is the empty string. How many sentences are in the language? How large is this language?
Infinite?
Infinitely large, yes.
Because n could be as big as we want it.
Yeah, and is unbounded, since it can be any value from 0 unbounded. It maps again to the natural numbers, and there are infinitely many of them. Examples of strings using the alphabet that are not in the language.
ABA.
ABA. What else is not in the language?
A.
AA. Not in the language. So AB was in the language, but there's nothing in this language that allows for any A's past that last B. Similarly, for every A, we have to see some following B at some point once the A's are done. We can't have some A's without those trailing B's. What's another different kind of string that is not in the language?
That mean like A, B, B, A would be not going to?
Not in the language, correct. A, B, B, A. They're the same number of A's and B's, but they do not adhere to that form. Good. Another one?
Yeah.
BA. Anything that starts with a B, automatically not in the language. So again, we'll come up with ways to describe all strings that are not in this language. All strings that are in this language will have a concise way of doing that soon. But for now, it's good enough to just know some examples, be able to make some examples. So we know that languages are just fancy sets. So we can define things like the union, intersection, and difference between two languages. Anything we can do to a set, we can also do to a language. We can define the complement of a language as just the star closure of the alphabet minus the language. Everything that is in the star closure of the alphabet but is not in the language is in the complement of the language. We can define the reverse of a language as just all strings such that if you reversed them, they would be in the language. So we can define it as such. The reverse of a language is just the reverse of all strings where that string was in the language. We can concatenate two languages by saying, all right, let's allow all strings where the prefix of that string comes from the first set, and the suffix of that string comes from the second set with no overlap. So that would look something like this. We'll define that as L1, L2, the concatenation of two languages, L1 and L2. all strings XY such that X is a member of L1, Y is a member of L2. And then just L to the N is a language concatenated with itself n times. Any language raised to the 0 power is just the empty set, is the set that contains the empty string, and that's it. L to the 1 is defined to be itself. L squared would be, looking back up here, it's like L1, L2, except it's LL. X would come from L, Y would come from L. L cubed is LLL. X, Y, Z, such that X comes from L, Y comes from L, and Z comes from L. We can define the star closure of a language. This just says that we're going to union together all of the concatenations of L at all levels. So L to the 0, union L to the 1, union L squared, union L cubed. Just any number of strings in that language, any number of times. Broken into those associated chunks. Which means we can define the positive closure of a language as just that entire expression minus L to the 0. Now the empty string is only in this set and the positive closure if the empty string was in the language.
Is this like the equivalent of every single possible combination for words? So like every single work of Shakespeare is like, if there's Shakespeare in this language, is in this language pretty much because of the language closure, or?
Kind of. English is difficult because we have spaces.
That's fair.
And in computer science, we don't necessarily have those spaces. You can imagine all of Shakespeare with the spaces and new lines and any, if it's a book, any of the broken hyphens that separate words, take all of those out and you would just have this long sequence of characters that are concatenations of English words.
Okay.
That would be in both the star closure and positive closure of the English language, as would anything spoken by anyone who speaks way too quickly. Any questions about languages for the moment? We will dive very deep into this and make many puzzles out of this in the near future. We can now talk about grammars, because this is something very important to programming languages. We know that grammars are what define what is syntactically legal and what is not syntactically legal. So let's take a look at how grammars apply to programming languages. We'll start, of course, with English, because there is a natural tie between the English grammar that you were forced to learn and programming language grammars, which you don't necessarily think about as you're learning the language, but they do exist. And in fact, I will show you the Java grammar here in a bit. But starting with English, we could make a simplified version of English if we said all sentences can be broken down into two components, a noun phrase and a predicate. Notice that these are all variables separated by these angle brackets. We have concepts that need further definition, but that's what this grammar is saying. A sentence is a concatenation of two variable components. It's very much like object decomposition. You would have a large object representing a sentence, and it would have two object fields that are a noun phrase and a predicate. We now need to further break down and define noun phrases and predicates. So we do that. A noun phrase is an article followed by a noun. A predicate is just a verb, and it's okay to do this. You don't necessarily need to have at least two variables defining another variable. It can help to just understand the scope of what naming conventions exist. We're only going to allow two words to be articles, the and a, but now note that they are in quotes rather than angle brackets, representing that they are now instantiations rather than objects. And nouns are going to be boy and dog. Verbs are going to be runs and walks. So questions I have for you. The boy runs. Is this a legal sentence according to this grammar?
Yeah.
With one asterisk that I don't intend here. There are no spaces in this grammar. Don't mean that, but if we're concatenating it, the boy runs. Speaking way too quickly, then that would be it. But yes, the intended answer to this is yes. We can take a sentence and we can break this down into kind of a tree that says we have sentence, and this sentence can be broken down into a noun phrase and a predicate. I'm getting lazy. The noun phrase breaks down into an article and a noun. The predicate becomes a verb. One possible article is the, so we can make a substitution for the word the. The noun can become boy. And the verb can become runs. And now we see the sentence kind of at this lower level. If we do a depth first search through this tree, you end up being able to reconstruct the sentence. Questions on kind of the process that you would go through to produce this sentence out of this grammar?
No. I could see how it'd be very difficult to like verify that that sentence does match the grammar though. That would.
We will talk about exactly how to do that later in this course. In fact, will be your programming projects, a good chunk of your programming.
Yeah.
Example of a sentence not in the language.
Runs, boy, dog.
Runs, boy, dog.
Yeah.
Yes, we have a natural order defined by these concatenations. So if we start with something that's not a noun phrase, it cannot be in the language, even if it only uses the instantiations that exist here. So anything that's not in these instantiations automatically not in this language defined by the grammar. But yes, anything in the wrong order. That's good enough for now. We can define the concept of a complete grammar. Complete grammar just allows for every sentence that is in the language. So we could make an incomplete grammar that would syntactically say that some of what's in the language is in the language, but to be complete, it has to be able to fully differentiate between what's in the language, what's not in the language. So another way to state that, if the grammar can generate the string, it is in the language defined by the grammar. If the grammar cannot generate a string, it is not in the language defined by the grammar. So the grammar becomes a one-to-one mapping of what's in the language. This is always possible. You can define a grammar for any language that's out there. Question is, can you do it efficiently? That becomes the subject of later discussion. So grammars usually start with the vaguest form and slowly breaks it down, exactly like object decomposition, down into smaller and smaller objects until you can instantiate those objects with actual symbols. It's very similar to recursive thinking. It's very similar to putting together any kind of depth first search. So all of your background and algorithms will be very useful for understanding a lot of what this course throws at you. The idea is to just reduce each concept down into more and more concrete pieces until you define kind of the building blocks of the language. What are those base level constructs? So of course, grammars exist for all major programming languages. Any idea or thought about how complex those grammars are?
I bet the one for C++ is ridiculously complex.
I will give you an example. As you can see from the size of the scroll bar, it might not be, I'm still in my slideshow. Get out of here. Size of the scroll bar, it's probably not quite the size that you would think. But basically, we have concepts that are identifiers, qualified identifier lists. And again, this is using a slightly different notation. I can blow this up a little bit so it's a little bit more visible. But here are all of the different definitions within the Java grammar. So we can define now a type as either a basic type or a reference type. The basic type being any primitive, a reference type being any object reference, the basic types, everything that you could write. Reference types have identifiers and type arguments. Here's the exact syntax for that. Modifier list, you probably learned and had to memorize this at some point for some class. What are all of those restricted keywords? These are the ones that modify. And it's not quite as long as you might think, and or it's way longer than you thought. But these are the rules that determine whether a program is syntactically valid in Java or not. Now look, all of our assignment operators. All of our infix operations. It's not the most useful thing to go look at. This probably doesn't get a ton of hits aside from professors in compilers classes wanting to show off what a grammar is. But it's very useful to see that every language that we use can be defined, the syntax of it can be defined by just a list of rules that break down the complexity of any Java program into its components. And then we can put those components together to say, is this syntactically Java or not? But yeah, that's it. That's the entirety of the Java grammar. Done. Which one are we on? We are there. Somewhere. There we are. So here's a snip from the book. I don't expect or want people to start here and memorize this. I'll mention it and we will talk about it because especially if you're reading the book, then it's good to be able to formalize your understanding of a grammar and be able to represent a grammar in terms of its components. But let's at least talk about how to read something like this in a textbook so that if you go try to reference this, we know exactly what it's talking about. So a grammar is defined as a for tuple, has 4 elements to it. We need to know 4 pieces of information in order to make this grammar distinct from everything else. We have a set of objects that we call variables. In our prior grammar example, this was just everything that was, I went too far. Everything that was a variable within this. So sentence, noun phrase, predicate, article, noun, verb. Those are all of the variables in the grammar. We have a finite set of objects called terminal symbols. This was the and boy and dog. It runs and walks, nay. So those are terminal symbols that you cannot break down further. They're the fundamental building blocks of the language. Then we have the start variable. Every grammar has to start somewhere with the most abstracted term. Sentence was that most abstracted term in the last grammar. There was no further abstraction from sentence. All sentences start as a sentence and then are broken down into components to be able to answer, yes, this is a sentence according to this definition, or no, this is not a sentence according to this definition. So the start variable tells us where do we begin that analysis at sentence in the last example. Then we just have a finite set of productions, which are every line there in the last grammar. Let's actually go back and look at that. So each production is sentence, arrow, noun, phrase, predicate. That is one such of those. Another down here, we actually are concatenating two of them together with this or. Article, arrow, the is one of them. Article, arrow, a is another. So those are all productions in the grammar. With those four pieces of information, we now have an object that represents this grammar without having to put in this grammar and have to parse it. If you put it in that order, it creates all the associated data that you would need to be able to look at, answer any question about this from a digital perspective. From a human perspective, it's much nicer to just look at the grammar, but if you're going to store a grammar internally, it makes much more sense to store it as this for tuple. You don't want to have to parse all of the productions or assume that the first production that is listed, the left-hand side of that is the start variable. Those are generally bad assumptions to make, although I will always be referring to them in that order. Let's give you an example grammar. So let's start with the question of what is the language defined by the grammar? So here is our for tuple. We know we have S as our only non-terminal symbol, our only object symbol. The terminals, the characters that are actually the characters in the alphabet are just A and B. We have S given as the start non-terminal, and P, this list, given as the set of productions. So as the grammar was written before, you can really just now look at this to say, what is the language defined by this grammar?
It's the A N B N.
A, B,
what
and
we
B
were
is
talking
again?
about earlier. Yeah.
Yep, it is. Did people see that? Did people see why this can produce an arbitrary number of A's followed by exactly that many B's? So we can start with this start non-terminal. From here, we can kind of branch. We can choose which of these productions we apply. On one hand, we can just apply lambda and we end up with the empty string and terminate because there's no further work to be done here. There are no non-terminals to break down into their associated components. On the other hand, we could make this substitution replacing S with ASB. Great. Now this has a branch because this S needs to be further defined and broken down. This S could be broken down into components. It could either go away, in which case we end up with AB, or this S could become ASB. Now it's just this S, so this A and B stay there. We have an A at the beginning, we have a B at the end, and now this S becomes ASB. This can be broken down further. You can continue and see that this sideways tree goes on forever. And each leaf node in this would just be a different string that is in the language. So you could start with the empty string. This path generates AB. This path would generate AABB. The next path would generate AAABBB, etc. Do note that there is a notation that is, if you wanted to say that this grammar can generate the string AABB via some set of productions, that is how you would write it. S arrow with a star on top of it says with some number of productions in some order, we can produce this string. Questions or concerns on this idea? Analyzing a grammar and figuring out what language it represents? All right, let's try a couple on our own. And possibly even go the other way. Find a grammar that generates the language A to the N, B to the N plus 1. So before we dive too deeply into this, let's come up with a little list of strings that are in the language. So what is a string that is in this language?
B.
B is in this language. A to the 0, B to the 1, N is 0. What else is in this language?
A, B, B.
A, B, B, this is N equals 1. What else? A, A, B, B, B. I think that's enough to get started, but you want to generate a grammar that produces and can produce if this sequence went on forever via some set of applications of those productions. You could generate any one of these strings with this pattern repeated forever. Try your hand at it. Introduce yourself to your neighbor and work together if you'd like. We don't hate each other in here like we do in software engineering.
Not yet.
Right, you got it.
I have an idea. What is similar to what we've just shown, I don't know. Okay, it's very so. Well, n equal to 0.
I don't know if they have access to the empty string notes.
So you've got you're repeating it, you just need to terminate rather than going to lambda. When I said tack on, that was me.
Well, that might actually be it. Maybe use like P.
And then S can be replaced by
A, and B or S.
It's
Yeah.
I think that's impossible. So you can. We'll tell you. Because this class is so hard. This is wait, so we have precedent being that. As long as your solution for S and B on set, then it works. But if that's called, C comes later. That's not an AS.
Small are A or S.
Yeah, but AS, I get that.
replacing.
But
Basically, same thing we have there. So I'm
this class goes so quick.
Yeah.
But it's because we just haven't those.
I'm trying to access the spread something like that. What about me? Like for this like us what it is.
Like there.
That's Chad. Chad is full power for the.
Only we all.
Just randomly without starting words.
That's
those brainwaves.
That's one day.
By the time my hair. By the time the tips of my hair is close to the white and red and where I'm sharp necklace. I was just something.
No,
Thankfully, I was with the tornado.
We have solutions?
Yeah.
A solution? Anyone else with a solution? Couple solutions? I'm curious what people have. Someone who has a solution, walk me through it. Raise your hand and I'll let you know. Yeah,
So the idea was, I assume you just want to know the production rules. right?
yes.
So the first one was capital S can be B, so S arrow B. And then the second one was capital S arrow A, capital S B. And it's basically just the same as what you showed us earlier, but with B instead of lambda. And I think that should work as long as N is greater.
How does we terminate? I guess, yeah, we can make this B at any point.
Mhm.
And that becomes the last B. And since this is in the middle, you're using recursive thinking to decide that when this does terminate, you're done.
Mhm.
I like it. I think this is the simplest possible response. There is another one that might make more intuitive sense to some that utilizes an extra non-terminal, and we will find that there are multiple grammars, just like there are multiple programs that can solve the same problem. There are multiple grammars that can represent the same language. So you could do something like S arrow, you don't necessarily just have this B, let's just say, we'll use another non-terminal. And then this can become So we generate that last B immediately. We know it has to be there. Everything here has at least one B at the end. We'll just throw it at the end, and then we will go into exactly what we had before, where we can now generate an arbitrary number of A's and B's recursing in the middle, eventually terminating with the empty string. So both of these are equivalent grammars. Which one you prefer is up to you. But there, as always, are multiple approaches to a right answer. You could make this arbitrarily complex. You could make a 20 non-terminal version of this if you really wanted to. Just like you can write a bunch of does nothing lines in a program and it's equivalent.
I kind of see how the second one is clearer because it kind of gives you like an entry point, so to speak. It's like you always start with that first production rule.
Yeah,
Whereas with mine, it's kind of like you gotta pick the right one for the simplest case of like just.
yeah. People think and learn differently. They break down problems differently. So whenever I can, I want to show a couple of different ways to approach a problem in case one is, it more closely aligns with how you logically decompose the problem and want to solve the problem. Neither one of these is significantly better than the other. The solution that I have on the slide is the one I wrote in the board. No, they're both here. So the second one just says that we can now redefine A in two ways, which is the reason that I used this slightly more complicated one. This just says A can be substituted with the left-hand side or the right-hand side. We'll get into what non-determinism is, but basically you can choose either one and it's correct. Some version of this program could go down either path. We can state that two grammars are equivalent if they generate exactly the same language. They accept the same strings and reject the same strings. All right, let's talk a brief overview of state machines, also known as automata. They're beautiful because they are abstract models of the kinds of computations that a computer can do. And they allow us to design programs almost at kind of a circuit level. It's very much like Boolean algebra and circuits, except that it's a little bit more complicated and can solve and eventually represent the entirety of what a computer can do if we use something complex enough. So what is an automaton? It converts input to output and may be able to store something along the way, depending on the type of automaton it is. So it needs some way to collect input. It has some way of reading the characters from an input string. We're going to read the string character by character from left to right, and we cannot go back, which means that at every character, we need to make some kind of decision or store something about whether this string is going to be accepted or rejected. The idea is that we're going to build a state machine to represent a language. And when this state machine ends in an accepting state, then the string is in the language. If the state machine terminates in a non-accepting language, in a state, then the string is not in the language. So as input, it has a way to produce output to a temporary storage device, some of them. So it may be writing something as it reads. We will not start with those state machines. There's also an internal control unit that keeps track of what state it is in. So we will define some number of states and transitions between those states. When you're in this state and you see an A in the input string, move from this state to that state. Something like that. It's a bunch of if-then rules that allow you to jump around inside of the control unit as the input is reading character by character And where this control unit stops at the end of the string determines whether it's in the language or not. So our task is going to be to design such a state machine for a particular language. So here's a visual representation of it. Start with an input file, utilize some storage, the control unit interacts with the storage, and eventually the control unit produces some kind of output, either just in terms of which state it finishes in, or it may actually be producing some output. So it very much is a model, a theoretical model of a digital computer, which is really cool. And if we're going to study compilers in general, then we need to know how the CPU works in order to be able to model something like this in terms of, at a high level language, how do we do that conversion down into verifying syntactically that this is correct? So we will operate in discrete time steps. At each time step, we will be in a particular state. So maybe we're in state 1, state 0, state 6, some state that the control unit is in. There will be a current character in the input symbol. What symbol are we currently parsing? And then the transition between time steps is just saying, given the input symbol that we're reading, what transition do we take? What state do we move to as we move past that character? That's going to be defined by the transition function that is just which state are we in, what character are we reading? As we transition, there may be some output rate. We can then define a configuration that tells us, all right, we can write now exactly where this state machine is. So we need to know what character we're on, what state we're in, the full input and output that it's produced. Then we can define the concept of a move as just a transition from one configuration to another. We'll talk about a bunch of different types of automata, since there are a bunch of different language classes. There are simpler automata types for simpler language types, and there are more complicated automata to represent more complicated language types. We'll start simple, and we'll slowly zoom out until we're looking at everything that a computer can do. And even some stuff a computer can't do. So there are two different basic classifications of automata, and we will dive into both of them, starting with deterministic. This just says that there is only one possible transition given the current configuration of the machine. If we're in state 2 and we see an A in the input, there is only one thing we can do. One possible transition. The nice thing about having a class immediately after this is they let you know when we're done. So we are officially out of time. So we will come back to this halfway through this sentence, halfway through this slide.
Cliffhanger.
Yes, and
What's a
talk about
non-deterministic?
non-deterministic automaton.
Suspense skill.
There are multiple options for where you can go.
Plot twist. They're all deterministic.
Yeah,
I'm not able to download the slides.
right. Yeah, I have not revealed it yet by hands.
Yeah, I can see it just as I can't download them.
Weird. I'll take a look at that.